Hi everyone. So in today's video, we are going to be talking more about the derivative function. So we're going to be doing another example of using the limit definition to calculate the derivative function. And then we'll be talking more again about that relationship between what the derivative tells you about your original function, as well as some other just kind of technicalities about derivatives. So we talked about last time how the derivative function, so if f of x is a function, f prime of x is its derivative function. And basically the point of the derivative function is that it tells you the slope of the tangent line, or another kind of maybe like more concise way of saying that is that it's the instantaneous rate of change at every single x value. So f prime of x tells you the slope of the line tangent to f of x. And as I said, another way of thinking about that is the instantaneous rate of change. So that's something we talked about at the beginning of the quarter, is that the slope of the tangent line is the same thing as the instantaneous rate of change. So like how, what's going on in your function at that moment? Is it increasing? Is it decreasing? How steep is it? That kind of stuff at that specific x value. So, or the instantaneous rate of change at every value of x. And we'll see that actually there are some exceptions. I shouldn't really say at every value of x, but I'm just going to stick with it for the sake of this definition. So you can think of the derivative function as being a function that kind of contains all of this information about your original function. It's like kind of stores all of this information about how your original function is changing. So the way that we calculated the derivative function is that we use that same limit definition that we had before, but the only difference is that whereas before we were doing the limit as h approaches 0, and then we did f of a plus h minus f of a, and we actually put in a number for a. Now we're just doing it with x, and we're going to leave x in there, and the point of that is that it's going to result in a formula that still has an x in it, and then we can plug in whatever x value we want into that formula. But this formula still comes from the same place, right? So it's still kind of this idea of the finding the slope of a secant line between a point and another point close by. It's just that now we're using x instead of a, and then we're still doing a limit as h approaches 0 to bring that second point closer. So I want to do an example. So let's let f of x equal x cubed, and we are going to find f prime of x. So this is one of them where I think it's kind of nice to, before you even, like, rather than jumping straight to the limit, actually just figure out what is f of x plus h first, because there's like a little bit more algebra to be done on this than on some other ones. So f of x plus h is going to be x plus h cubed. So that's x plus h times x plus h times x plus h. And there's a variety of different ways to multiply this out, but the way that I'm going to do it is we can first multiply together these second two, and then multiply that together with x plus h. So if you multiply just the second two together, you'll get x squared plus 2xh plus h squared. And now we can multiply in the x plus h. And so we're going to get x cubed plus 2x squared h plus h squared x. And now we multiply h with everything, so we get plus hx squared and we get plus 2xh squared, and then we get plus h cubed. So even though that has a lot of parts to it, there actually are no common, there's nothing that you can combine. They all kind of look similar, but if you look closely, they have different numbers of x's and h's in them. Okay, so sorry, that might go slightly off screen for you because of how I have the screen cropping set up. But let's put this together. So now we have the limit as h approaches 0 of, so we want f of x plus h minus f of x divided by h. And so in this case, that's going to be the limit as h approaches 0 of, and we just found over there, so x cubed plus 2x squared h plus h squared x plus hx squared plus 2xh squared plus h cubed. And then from that, we are subtracting x cubed because that's our f of x, and that's all divided by h. So what you might notice here is that what's going to cancel out, so just like on some earlier problems that we've seen, the parts that don't have h's in them are going to cancel out, right? We have an x cubed here, we have an x cubed here, and so we're going to be left with, everything that we're left with is going to have an h. So we have the limit as h approaches 0 of 2x squared h plus h squared x. I know this one is kind of a lot. Plus hx squared plus 2x h squared plus h cubed, dividing that by h. So now we can go through and kind of get rid of all these extra h's. So here this is going to become just h. This one is going to go away. This one is going to become h, and then this one is going to become h squared. So we're going to be left with now the limit as h approaches 0 of 2x squared plus hx plus x squared plus 2xh plus h squared. So now we can plug in 0 for h, right? And so when we do that, we're going to get, basically just looking through, like the only part that's actually going to stay is going to be this and this, right? Because everything else has an h in it. So I just wanted to point that out. So we're going to be left with just 2x squared plus 0 plus x squared plus some more zeros, and then that gives us altogether 3x squared. So that tells us that the derivative function of x cubed is 3x squared. So I want to again do a little side-by-side comparison to kind of talk about what the derivative tells us about the original function. So here is our function. So this is f of x is equal to x cubed. Hopefully you know what that graph looks like. And then our derivative we know now is 3x squared, so that's going to be a parabola, and I graphed it ahead of time and I have it hiding over here somewhere. Let me just grab it and bring it down here. Okay, so here's our derivative function. So this is f prime of x is equal to 3x squared. So I just want to again see kind of what are the connections between these and really try to make some of this stuff explicit. So one thing I just want to emphasize is the fact that every point on the derivative, if you look at it, it kind of tells you something about a point on the original function. So for example, if I go to this point here, this is the point 1, 3. That tells me that and maybe let me even write this down. So because the point 1, 3 is there, that means that f prime of 1 is equal to 3, right? Because that's how functions work. The x value is the input, the y value is the output. And so our function is f prime of x, so f prime of 1 is equal to 3. And so that tells us that the slope of the tangent line at x is equal to 1 is 3. And so what that tells us, and that doesn't, not the tangent line to this graph, the tangent line to our original graph. So that means that if we were to go to an x value of 1 here and actually sketch a tangent line, and you can kind of, that looks like it has a slope of 3, right? So this would have a slope of 3. So that's what I mean when I say that every point that is on the derivative function tells you information about your original function. The other thing that we talked about last time was this idea of like increasing, decreasing, and 0, and I want to reiterate that part. So I feel like this might be helpful, so maybe I'll leave this here and just copy the images so we can do something else on them, because I like having that kind of like really explicitly said fact about the derivatives there. So I'll leave there. Okay, so the other thing that we talked about last time was that basically based on the same thing that we just said above, if you look at that parts of your original function that are increasing, so this part of your function, actually basically the whole function except for 0 is increasing, right? So maybe I'll write that a different way. So I'll say that this is increasing at all x values except at 0. And so what do I mean by that? I mean that it's going up. You know, if you were to look at the slope of a tangent line at any x value, it would always be positive. The graph is never going down. The only exception is that when x is equal to 0, the tangent line would actually be horizontal because the graph kind of temporarily flattens out for a moment at 0. And so that lines up with what we see in this picture, which is that if you look at the y values of the derivative function, those are all positive y values. So this function is positive at all x values except at x is equal to 0. So I said this last time, but I really want to emphasize it because I found when I've taught this class in the past, people kind of get confused between what increasing means and what positive means. When I say positive, I literally just mean that the y values are above the x-axis. So for example, the graph on the left, the original function, is not positive everywhere, right? This part of the graph is actually negative. But if you look at the derivative function, every single part of the graph lies above 0 except for the part that is actually at 0. So increasing is talking about whether it's going up or going down. Positive or negative just means literally is it above or below the x-axis. So other thing we can add here is that it is neither increasing nor decreasing at 0. So when a graph is neither increasing nor decreasing at a particular x value, that tells you that the derivative is actually equal to 0. So we should just say the derivative is equal to 0 at x is equal to 0. So when I say equal to 0, I mean, again, the y value of the function is equal to 0 when x is equal to 0. So those facts that we wrote down are true in general, and I just want to summarize them. And this is something that is really important, but we'll also be definitely coming back to it a lot. So this is just kind of the first discussion of this idea. So in general, if f prime of x, or actually let me say it this way. I'll say if f of x is increasing, and I apologize, my headphones that I'm using as my microphone just gave me a notification that the battery is dying. So there is a chance that the audio will kind of drop in quality partway through this video. So I apologize for that. We'll see how it goes. So in general, if f of x is increasing, then f prime of x is greater than 0. So meaning, again, the y values of the function are positive. if f of x is decreasing, oops, not f double prime, we didn't get there yet. F prime of x is less than 0, and then if f of x, I'm just going to write, is neither increasing nor decreasing, it's kind of flat, then the derivative is equal to 0. Okay, so there's something else I just want to briefly talk about, which is that, I just sort of said, like I just sort of jumped into saying that you can take the derivative of a function. There are certain situations in which you cannot take the derivative of a function, so that's the next thing I want to talk about. So a function, and I'm sorry that I'm guessing that actually you all could hear when it said battery low, because the part where the sound is coming out in my headphones is right next to the microphone. So you probably heard that, and you'll probably hear it again a few times throughout the rest of this. So a function f of x is called differentiable. Oops. Differentiable at a particular x value. So I'll just say at x is equal to a if f prime of a exists. So basically, saying that a function is differentiable basically just means that you can take the derivative. So maybe I'll even just write that, i.e., you can take the derivative. So why could it, why would it be that you could not take derivative? Well, think about how the derivative is supposed to be the slope of a tangent line. And so basically, we'll see that the situations where the derivative does not exist is going to be places in the graph where it would not be possible to draw a tangent line. So let me see how I want to say this. So I'll say f of x is not differentiable at x is equal to a in if any of the following occurs. So the first case would be if there is if your original function is just straight up undefined. So if the original function is undefined, then there cannot be a derivative, right? That just kind of makes sense. And so that means you could have like a hole or a vertical asymptote, or the graph could just literally not exist at that part. So if your original function doesn't exist, there is no derivative. Second case is if f of x has a corner, or, and I'm going to put a word that maybe you haven't seen before, cusp, and I'll explain what I mean by that in a second, at x is equal to a. So a corner would be something like what you see in an absolute value graph. So a corner would be something like, this. If you have f of x is equal to absolute value of x, that function would not be differentiable turned off. And I'm actually going to stop the video for a second to check my audio, and I'm probably going to have to stitch this together with another video, but let me just go and check if my audio, it looks like my audio is still working, so I'm going to keep going with this, and it might sound a little worse, but I'm going to try to just keep going. Okay, so this function is not differentiable at x is equal to 0 because the graph has a corner at that part. And so why is this an issue? Well, basically, if you were to try to sketch a tangent line at 0, the problem is that there isn't really like a good kind of direction to go with, right? So like the first part of the graph is kind of going down in a negative direction, it would have a slope of -1. And the right-hand part of the graph has a slope of +1. If you were to try to draw a tangent line at this corner, how would you know where to draw it? Like, would you draw it like that? Or would you draw it like this? Or would you draw it like, oops, not like that. Or would you draw it like, you know, this or like this or like this? Like, there's just too many options. Because it's a corner, you just can't really like define what the direction is of that corner. So anytime you see something that's kind of pointy like that, it does not have a derivative. So similarly, if you have the function, so this is x to the 2/3, looks like this. So that's what's called a cusp. So x to the 2/3, so that would be the same thing as the cube root of x squared. So again, that would be not differentiable at this corner or this cusp at x is equal to 0, because again, if you tried to draw a tangent line, it just isn't clear like where it would go, right? There's just too many different possibilities. Whereas if you were to go at different parts of the graph, like, you know, let's say here, it's pretty clear like what is the direction of that graph, or like here, or, you know, you can kind of follow along with it. But at a corner, it just doesn't, it's almost like you're trying to balance something on like a pointy end and you just don't really know where it's going to balance, if that makes sense. Okay, so those are kind of the two most common ones, but let me just say one more thing, which is if your graph actually has kind of an end point, so an example of that would be when we did the graph of, or the derivative of the square root of x. So the square root function, the graph of it looks like this. And basically, because it's not defined for any number that's less than 0, it just kind of ends at 0. And so this function, f of x is equal to square root of x, is not differentiable at x is equal to 0 because it has an endpoint. I know all of these have x is equal to 0. It doesn't have to be x equals 0. It's just the way that these graphs are positioned. Okay, so I want to just look at one quick example to see like some cases of where a graph wouldn't be differentiable. So for example, if this was your function f of x, so this is an example. So if this is your function f of x, then you would say in this case that f of x is not differentiable at x is equal to -2, right? Because that's an endpoint. You couldn't like draw, you know, one specific tangent line at that endpoint. It would not be differentiable at x is equal to 1 because again, like you have this issue where like you can't tell where the tangent line would even go. It would not be differentiable at x is equal to 3 for the same reason. It would not be differentiable at x is equal to 4 because that's one of those kind of cusp shapes. And it would also not be differentiable at x is equal to 6 because that is another endpoint. So in practice, most cases that we see are not really, we're not going to really deal with too many examples of functions like this that have so much going on. Probably the absolute value graph is kind of the most common thing that we'll see, or more just like being aware of, you know, if your original function is undefined at a particular value, that the derivative will also be undefined. And then I think also like the square root graph is a good one to know, right? Because the square, we saw that actually the derivative of the square root graph, if you go back to the video from last time, you'll see that it actually, the derivative function has a vertical asymptote because the derivative function is not defined when x is equal to 0. Okay, so one more quick thing I want to do, and then we'll get into some examples, which I just realized are not here. Let me, okay, I'll get there in a minute. But yeah, I wanted to talk about derivatives of linear functions. So this is actually something I asked you to think about on your worksheet from last time, was I gave you a linear function. I asked you to find the derivative at a particular point. And then I asked you, like, why was that kind of a waste of time? Like, why did you not really need to use the limit definition? And so the reason is that, remember that the derivative tells you the instantaneous rate of change at any point of your function. And if you think about way back at the beginning of the quarter, we talked about how linear functions are really actually the only type of function that you already know what their rate of change is. Their rate of change is always the slope. So I'll kind of summarize that as saying if f of x is equal to mx plus b is a linear function, then the derivative is just equal to whatever the slope of that line is. And so what that basically tells you is that if your original function is a linear function, then the derivative function is a constant function, right? So for example, if your original function is, let's say, negative 5x plus 1, the derivative is just going to be negative 5. And so remember, the way that a constant function works is that no matter what number you plug in for x, you get the same result. And that makes sense, right? Because whereas if you go back to some of the other examples we were doing, like this function, the x cubed graph, has different slopes everywhere. So it makes sense that the derivative function has different y values everywhere. Whereas if you have a linear function, it has the same slope everywhere. And so it makes sense that its derivative is just like this constant number. The derivative never actually changes. Let's just actually even just sketch the original function and the derivative just to really kind of drive home what we're trying to say here. So the original function would be negative 5x plus 1. So I'm just going to kind of eyeball that. So that would be a slope of negative 5 and a y-intercept of 1. So, some steep. And I know that looks like it goes through 0, 0. That was not the intention. Let's just say something like that, right? It's a line that has a slope of negative 5 and a y-intercept of 1. And so what would the derivative look like? Well, what does the graph of f of x is equal to negative 5 look like? It's literally just a horizontal line through a height of negative 5. And so that, again, fits with this idea that any x value you go to, the derivative always has a value of negative 5. Whereas any x value you go to on your original function, the slope is always negative 5. So there's still that same connection that we saw on the previous example. Okay, so last thing I want to look at is an exercise that I think is challenging, or at least most students find it pretty challenging, but I think it's really good practice for trying to really drive home that connection between the original function and its derivative. So what we're going to do is I'm giving you right here the graph of a function that we're going to call f of x. And we're going to try to use this graph to sketch the graph of the derivative function. So it doesn't have to be perfect. If I'm asking you to do something like this, like let's say on a quiz or on the homework or something like that, I'm not looking for absolute perfection. I'm just kind of looking for the right general idea. So I'll show you what I mean. So let's say that, again, let f of x be the function graphed. And so we are going to sketch the graph of f prime of x. So a good place to start is to look at where are the places where the original function f of x, where does that graph have a horizontal tangent line? Because if the original graph has a horizontal tangent line, that means that the derivative equals 0, right? Because horizontal lines have a slope of 0. So it looks like when x is equal to 0, there's a horizontal tangent line. And so that tells us that the derivative should go through a height of 0 at that point. Same thing when x is equal to 1, right? When x is equal to 1, we also see that there's a horizontal tangent line. And then finally, same thing when x is equal to 2. We have a horizontal tangent line. And so the derivative should be equal to 0 at that x value. So we already know like 3 points that definitely lie on the derivative graph. So the next thing, and this is where it kind of, it doesn't have to be perfect, but we want to kind of try to get the right idea, is we want to look at where is our original function increasing and where is it decreasing. And we're going to use that to figure out where the derivative is going to be positive and where it's going to be negative, right? So if you look at the function f of x, the function f of x is increasing basically from negative infinity. Let's assume that this graph kind of just keeps going in those directions. So it's increasing, increasing, increasing. Then it is decreasing here. I'll just write decreasing. Then it is increasing again. And then finally, it is decreasing again. And so what does that tell us? That tells us that the derivative function should be positive, and then it should be negative, and then it should be positive again, and then it should be negative again. And so I'm just going to kind of draw something here, and then we'll tweak it a little bit, but we know that basically it's going to be like, so positive, then it has to go to 0, then it's going to be negative, then it has to be positive again, and then it has to be negative again. So something like that. So does everyone see where that's coming from? So basically I'm trying to sketch this graph so that the y values are positive at the parts of the original function that is increasing. So it's positive up until we get to 0. Then it's supposed to be negative because this is the part of the graph that is decreasing. And so I'm going negative, but then at some point it has to turn around to go back to 0 again. And then similarly here, it's positive, and then it has to turn around at some point to go back to 0, and then it's negative. So how could we figure out, how it may be like a little bit better, how far down or how far up it should go? Well, we can look at what looks like the maximum and minimum slope. So I would say, let's get rid of the middle part for a second. So I would say that for the first part, it looks like the further you go this way, the steeper the graph gets, right? So that means that basically our derivative probably kind of looks like this. It's getting, the further you go to the left, the higher and higher those derivative values are going to get because the graph is getting steeper and steeper. And similarly, on the right side, the graph is getting steeper and steeper in the negative direction. So that means that the derivative is probably going to go down like that and get more and more negative as it goes. And so then to figure out like what is the, how low and how high should these points go, let's try to figure out what looks like maybe the steepest value that happens in this part of the graph. So to me, I would say it looks like, so a slope of 1 or -1 would be like that, right? And it looks like it gets a little bit steeper than that. So maybe let's have it go down to like just a little bit more than -1. And then similarly here, we see that the slope looks like it gets in the middle there somewhere a little bit steeper than +1. And so that means that the derivative should go a little bit higher than +1. And it should really kind of be the same as the other one. So let me tweak that a little bit. So let's say that this was on, like a test or a quiz or something. I wouldn't really care so much about exactly what this part of the graph looks like. What I would be looking for is, did you make the graph pass through 0 at the right parts? Did you make the graph positive at the right parts and negative at the right parts? That's really all I'd be looking for. Okay, so let's do one more, and this one is a little bit different. In some ways, it's definitely easier. In some ways, I think some people might find it a little trickier. So let's maybe call this one g of x. Be the function graphed. And we are going to sketch the graph of g prime of x. Okay, so why do I say this one is easier? Well, basically, whereas we had to kind of do some guessing games on this one, right, and kind of estimate stuff, on this one, we actually know exactly what the derivative values are, because if you look at this function, it's made up of pieces that are all lines. And we know that linear functions, the derivative is just the slope of the line. So basically what we can do is just go through and look at each different segment of this graph and record what is the slope of that segment of the graph. So for example, the first part of the graph, so this part, has a slope of 2, right? And so that means that any x value between 0 and 2, the slope is 2. And so what that means is that our derivative should be a horizontal line at a height of 2, which I didn't make quite horizontal. Right? Because again, like you want to think of, if I were to plug in any x value to the derivative function, I should always get 2. And that's exactly what it means to have a constant function or a horizontal line. Okay, what about this next part? So this part of the graph. So this next part of the graph has a slope of 0, right? So this part of the graph, if the whole graph was just a horizontal line, its derivative would just be f prime of x is equal to 0. And so we have to think about, what is the line, if I were just to tell you graph, h of x equals 0, what would that look like? It would be a horizontal line at a height of 0. So the derivative for the middle part would just be a horizontal line at a height of 0. Finally, this last part has a slope of -1. So we would want to make the derivative just a horizontal line at a height of -1. So there's one more thing that we can add to this, and it's kind of a technicality. I wouldn't worry too much about it, but technically the derivative is not defined at any of these points, right? These are both kind of corners, and then these are endpoints. And so the way that we can denote the fact that the graph is not differentiable at those points is to basically leave them out of the derivative. So the way that you typically will, like, if you want to leave a point out on a graph, you add like an open circle. So maybe let me just adjust this a little bit. Oops, I accidentally changed color. So instead of having this go all the way, we can put this hole there. So when you draw a circle like that on a graph, it's like kind of it's almost like a cartoon. It's an exaggeration to represent the fact that this function is valid all the way up into, but not all the way up until 2, but not actually at 2, because the slope of this this line is 2, it's 2, it's 2, it's 2, it's 2, but then as soon as you hit this point here, the slope is not 2 anymore, and the slope is actually undefined, and so that's why we're putting that open circle there. And then similarly, at this one, we want to actually put kind of open circles on each end of it. And then actually I left it off here. We should have put an open circle on the end here, an open circle. I'm getting a little lazy. Let me do that a little better. Open circle here, and then another open circle here. So I wouldn't worry too much about the whole open circle business, but the point is basically just to reflect the fact that the original function derivative is not defined at those points. And I just realized a mistake I made, which is for some reason I shifted this whole part over. So this actually should have been here. Sorry about that. Right, so the part of the graph where the slope was -1 should have been from 3 to 4. And so I'm not sure why I drew it over there, but it should have been over here. All right, that's it. Sorry for the hiccup with the headphones, but hopefully I came through audibly to all of you. And so tomorrow we're actually going to learn a shortcut that will let you find derivatives of functions in a much faster way. So if you've taken calculus before, you probably know what I'm talking about. There's basically rules that you can use to take derivatives rather than having to use the limit all the time. That being said, don't disregard everything that we learned. You do need to know how to use the limit definition. In the future, we'll basically be using these other shortcut rules a lot more frequently, but you do actually still have to know how to use the limit definition. All right, so I will see you all in the next video.